Imagine a computer so powerful that it could simulate molecules perfectly, break certain cryptographic codes, or solve optimization problems that would take real computers thousands of years. But that's the promise of quantum computing. But to understand how these quantum computers work, we need to know one fundamental concept: the quantum gates. These gates are sort of the building blocks of quantum algorithms, and without them, quantum computing just wouldn't exist. So let's start with regular computers. In these computers, information is stored in bits. A bit is either 0 or 1. Logical gates, like AND, OR, and NOT, manipulate those bits to perform calculations. But quantum computers work a bit differently. Instead of these bits, they use what we call a qubit. A qubit can be 0, 1, or both at the same time, thanks to a property called quantum superposition. This means that quantum systems can represent many possibilities simultaneously. But representing this information is only half the story, and is what people think is the entirety of quantum computing. To actually process that information though, quantum computers need what we call quantum gates. A quantum gate is an operation that changes the state of one or more qubits. These operations are based on the mathematics of quantum mechanics, and they manipulate probability amplitudes rather than these simple binary values. One of the most famous quantum gates is what we call the Hadamard gate. When applied to a qubit, it places a qubit into superposition. Basically, it transforms a definite state into a combination of states, allowing the quantum computer to explore multiple computational paths at once. Another crucial gate is the CNOT gate, or the controlled NOT gate. This gate links two qubits together and creates a phenomenon known as quantum entanglement. When qubits become entangled, their states are interconnected. So that means a state of one qubit affects the other, even if they are far apart. This entanglement is one of the key reasons quantum computers can outperform classical computers for certain problems. Quantum gates also rotate qubit states in complex ways, using gates like the Pauli X gate, Pauli Y gate, and the Pauli Z gate. These operations allow quantum algorithms to carefully manipulate probability amplitudes, amplifying correct answers and canceling incorrect ones. This is how famous algorithms like Shor's algorithm for factoring large numbers and Grover's algorithm for searching databases achieved their speed advantages. Think of quantum gates as the choreography of quantum computing. By combining many quantum gates into circuits, scientists can build quantum algorithms that exploit superposition and entanglement to solve problems in new ways. However, designing these circuits is extremely challenging. Qubits are fragile and easily disrupted by noise from the environment. This means that quantum gates must be executed with extreme precision. Researchers at companies like IBM, Google, and Rigetti Computing are working to improve quantum hardware so that the gates become more reliable and scalable. The better the quantum gates, the more powerful the computer. So in the end, quantum computer isn't just about having these qubits, it's about how we control them. This control ultimately comes from our quantum gates. They are the fundamental operations that turn quantum physics into computation, and without them, quantum computers would just be strange physical systems. With them, they become machines that could redefine what computing is capable of. If you guys enjoyed this video, make sure to like and subscribe. Be curious like a child, the world needs more of it. Bye.